Addition angle identities proof. We need to prove these identities. If I simplify them a little, so we have sine A plus B and cos A plus B, tan A plus B, we get these identities. So we need to prove sine A plus B gives you this, and that cos A plus B gives you this. So we're going to draw some diagrams with triangles, and from there we'll work out where these identities come from. To get the one for tan, we're just going to do sine over cos is tan, so we're just going to divide, and then this identity will come through. The ones for the sine A minus B and cos A minus B, tan A minus B have a very similar method too. So first of all, we need to recap on right-angled triangles and SOHCAHTOA. So if I'm looking for the length of this unknown side here, so I need a relationship between the angle, the adjacent side, and the hypotenuse. So I need to use the cosine function. So cos alpha is equal to the adjacent over the hypotenuse. So if I rearrange, then my unknown side here is equal to 10 cos alpha. And we can do the same thing for this unknown side here, y. So now we need a relationship between the opposite side, the hypotenuse, and the angle. So this time we have sine alpha is equal to y, the opposite side, over the hypotenuse. So then we can say that y is equal to 10 sine alpha. So a quicker way to apply this is, if you know the hypotenuse and the angle, the adjacent side will be the hypotenuse, whatever that is, times cos alpha, and the opposite side again will be the hypotenuse times sine alpha. So in this triangle, if the hypotenuse is of length t, then the adjacent side will be of length t cos alpha, and the opposite side is t sine alpha. In this triangle, the adjacent is 1 cos alpha, and the opposite side is 1 sine alpha. The 1's are not doing anything. The hypotenuse was offside 1, so I can remove the 1 from here and here and simplify to just cos alpha and sine alpha, and this is quite useful for what we're going to do next. Now this might look a bit odd, but let's assume that the hypotenuse here is of length cos beta. So then the adjacent side will be cos beta times cos alpha. It's just the hypotenuse times cos alpha, which is this. The opposite side will be the hypotenuse times sine alpha, which is this. So I'm going to try and show you a proof for sine A plus B, or you can call that alpha plus beta, like I will in my example, and cos alpha plus beta. We need to show where the right hand side comes from for each of these identities. So I'm going to slowly build up this diagram, which will help with the proof. In this right angle triangle, the hypotenuse is of length 1 unit, so the adjacent side is 1 cos beta, or just cos beta because we're multiplying by 1, and the opposite side will be 1 sine beta, or just sine beta, like this. Now I've added on a second right angle triangle with angle alpha here. So if we just focus on our new right angle triangle, so cos beta is the length of the hypotenuse, so the adjacent side here is the hypotenuse times cos alpha. So cos beta, cos alpha. The opposite side will be the hypotenuse times cos alpha. So this will be cos beta sine alpha. Okay, so hypotenuse times sine alpha for the opposite, and hypotenuse times cos alpha for the adjacent. So if I bring the whole diagram back, we have this. Now so far I have two triangles with an angle alpha in one of them and beta in the other. I need a triangle with both alpha and beta in it, so I need to draw a vertical line from E going straight down to draw a new triangle like this. So you can see in this new triangle there's a right angle here, and this angle here is alpha plus beta. I've added another line here to create yet another right angled triangle, and you'll know something about Z angles. So that angle there and the angle that will be here will be exactly the same. You can see that this is a Z, so the angles will be the same. So the angle right there will be alpha. There is a 90-degree angle here, so the angle on the other side here, this will be 90 because it's a right angle minus this angle, so this will be 90 minus alpha. So the angle here will be 180 because I'm looking at the triangle here. So angles in a right angle add up to 180. So 180 minus 90 minus this angle, 90 minus alpha, that should be in brackets. Expand the brackets and these cancel, and the minus alpha, we're left with alpha. So this angle here will be alpha. Let's switch our focus to this triangle. So I'm going to remove the rest of the diagram and just focus on what's highlighted in green. So we know the hypotenuse, we know an angle. This is the adjacent side, so we have this sine beta times cos alpha to give the adjacent, like this. That's the cos alpha, and there's a sine beta multiplied together. The order in which you multiply them doesn't make any difference. I could have written that as sine beta times cos alpha. It's the same thing. And this side here is opposite the angle, so this will be sine beta times sine alpha, or sine alpha times sine beta. So now we have a very complicated looking diagram. Now if you focus on the green triangle now, the largest triangle with the angles alpha and beta in there, if we isolate that triangle, we know the hypotenuse. The adjacent side will be hypotenuse times the cosine of the angle here. So it will just be 1 times cos alpha plus beta, and the opposite side will be 1 times sine alpha plus beta. The 1 times doesn't do anything, we're just multiplying by 1, so simplified we've got these. So I know the length here in terms of alpha plus beta, the combined angle, the addition angle. What I need is the same length given in terms of the separate cos alpha, cos beta, sine alpha, sine beta terms. Okay, so for the sake of convenience, I'm going to move some of these labels like this, just move them out of the way. And then here we are back to our original diagram. Here are the labels that I've just moved out of the way. This one and this one. And from the diagram we can see the length of the green line is equal to the sum of the lengths of the two yellow ones. So sine alpha plus beta, this length, is equal to sine alpha cos beta plus cos alpha sine beta. So we have this identity. This is the first one. And along here and here, we can see that cos alpha plus beta, this length, is equal to all of this length, which is cos alpha cos beta, minus this length, sine alpha sine beta. So we get another identity, which is this. And now I'm going to multiply, and you can see that my numerator and denominator, I know I've got a fraction within a fraction, but if I look at the overall picture here, those two are exactly the same, so I'm essentially multiplying by 1. So I'm going to multiply my numerator by this term and my numerator by this term, and I'm going to do the same with my denominator. I'm going to multiply it with this term and with this term, so I get this. Then various terms will cancel, like that cos beta will cancel there, cos alpha cancels here, cos alpha cancels, and we've got various terms that will give us tan. I know sine over cos, so that's going to be tan alpha right there. Sine over cos, that's going to be tan beta. These two are the same, they've cancelled as well. So that's just 1. This fraction here gives you 1. And then I've got sine alpha over cos alpha, that's tan alpha. And I've got sine beta over cos beta, which is tan beta. So simplifying all of these, we now get this. So you've got tan alpha, tan beta, these were identical, so 1, and then we've got tan alpha, tan beta. So we've seen all 3 of these double angle identities, called addition angle formulae as well.